In today's lecture, initially I will talk about combinational logic gates in complementary metal oxide semiconductor, and then later we will focus on the discussion of stick diagrams and Euler graphs. Combinational versus sequential logic gates. In a combinational logic circuit, the output entirely depends on the current state of the input, while in a sequential logic gate, the output depends on the current state of the input, but it also depends on the previous state of the input. So sequential logic gates actually involve memory, while combinational logic gates do not involve memory. Examples of combinational logic gates are half adder, full adder, magnitude comparator, multiplexer, and demultiplexer. While examples of sequential logic gates are flip-flops, register, counter, and clocks. I want to show a comparison of static versus dynamic complementary metal oxide semiconductors as well. In static CMOS, we have a combination of two networks. We have a combination of pull-up network and pull-down network. The pull-up network is comprised of PMOS transistors, while the pull-down network is comprised of NMOS transistors in order to implement logic functions in integrated circuits. On the other hand, dynamic logic uses a clock signal for the implementation of Boolean functions and combinational logic circuits. Mostly it uses a clocked PMOS pull-up transistor, and because we have less number of PMOS transistors in dynamic logic gates, generally dynamic logic circuits operate faster as compared to static logic circuits, because in PMOS we generally have higher resistance, and because in order to cater for the resistance we need wider width of the transistors, which increases the capacitance of the PMOS transistors. So generally we have high RC time constant in PMOS transistors. So if we have less number of transistors in a particular CMOS logic circuit, then it's going to operate faster. And that's why, since we have less number of PMOS transistors in dynamic logic circuits, it operates much faster as compared to a static CMOS logic circuit. Here is an example of a static complementary metal oxide semiconductor where we have a pull-down network, which is a combination of the NMOS transistors, and a pull-up network, which is a combination of the PMOS transistors. Here is an example of a NAND gate. The inputs A and B, the NMOSes are in series, while the PMOSes are in parallel. Here we have an example of a dynamic CMOS circuit, which involves a clock signal. So initially assume that the clock is low. It means that this PMOS is conducting, while this clock is also connected to this NMOS transistor. So it means that this NMOS transistor would be, since the input is low, the NMOS transistor would be open. So this PMOS is conducting, while this NMOS is not conducting. It's open. So the output would be connected to VDD using this PMOS transistor. But since this path is open, the output is going to stay high irrespective of the state of the two inputs A and B. This phase of the dynamic CMOS circuit is called the setup phase, or we can also call it the pre-charge phase. The second phase is called the evaluation phase, in which when we turn the clock high, this PMOS transistor now is open, and this NMOS transistor starts conducting. So depending on the states of the input, we can pull down the output to the ground. Generally, static CMOS circuits consume less power as compared to dynamic, while dynamic CMOS circuits are faster as compared to the static CMOS circuits. In a complementary metal oxide semiconductor circuit, we have a combination of two networks, a pull-up network and a pull-down network. In the pull-up network, we have series and parallel combination of PMOS transistors, while in a pull-down network, we have a series and parallel combination of NMOS transistors. The pull-up network is connected to VDD, and the pull-down network is connected to VSS. And the pull-up network comprises of PMOS transistors because PMOS devices generate strong ones. They can be pulled all the way up to VDD, while NMOS transistors are used as pull-down transistors. They are used in the pull-down network because NMOS transistors produce strong zeros. It means that if we use NMOS transistors in the pull-down network, we can pull the output all the way to 0. Similarly, if we use PMOS transistors in the pull-up network, we can pull the output all the way up to VDD. But the other way around does not really work. If we use NMOS transistors in the pull-up network, we cannot pull the output all the way up to VDD. Similarly, if we use PMOS transistors in the pull-down network, we cannot pull the output all the way down to 0 volts. And let us try to understand this with the help of an example. And for that purpose, I need to perform some drawing. Unfortunately, I'm working on a desktop computer, so I have to use MS Paint in order to demonstrate this concept. Initially, let us try to pull the output to VDD, to the supply voltage. So for that purpose, initially, let us try to do it with the help of a PMOS transistor, and then we'll try to do it with the help of an NMOS transistor. So assume we are working on 2.5 micrometers technology, for which VDD will be equal to 2.5 volts. And pardon my drawing is not that great, especially if I'm working on MS Paint. So this PMOS transistor would start conducting if the input is low. So assume that the input is connected to ground, or assume that the input is 0 volts. Similarly, our output is over here. Generally, we know that here we would have the gate of the PMOS transistor. The source of the PMOS is connected to VDD, and the drain of a PMOS is connected is going to be connected over here to the output. So our VGS would be equal to 0 minus 2.5 volts, or minus 2.5 volts all the time, irrespective of the output. Once this transistor starts conducting, the output would start charging initially from 0 to 0.5 volts, 1 volts, 2 volts, and finally to 2.5 volts. Because VGS is equal to minus 2.5 volts. It's above the threshold voltage. In a 2.5 micrometer technology, the threshold voltage is around 0.4 volts. Or to be more exact, I would say that the magnitude of the threshold voltage is around 0.4 volts for 2.5 micrometers technology. Excuse me. So since this voltage VGS is above the threshold voltage all the time, so we can pull the output all the way up to from 0 volts to 2.5 volts. This would be 0 volts and this would be 2.5 volts. Now let us see, so if we use PMOS in the pull-up network, we can pull the output all the way up to 2.5 volts. Now let us see if we can do it in with the help of an NMOS. So for that, let me try to use an eraser so that I can draw an NMOS. For an NMOS, the drain is connected to VDD. So here is our drain, here is our source for the NMOS, and also the NMOS would start conducting if the input is high. So in this case, the input is going to be 2.5 volts. So it means that initially, so the input is high, this NMOS would start conducting. Initially, the output is at 0 volts and is going to start charging. When the output is at 0 volts, then VGS is 2.5 minus 0, it's equal to 2.5 volts. Then it starts charging to 0.5. So VGS becomes 2.5 minus 0.5 equal to 2 volts. Then it's going to charge up to 1 volt. So VGS becomes 2.5 minus 1 equal to 1.5. Then it's going to charge up to 1.5 and up to 2 volts. So VGS becomes 2.5 minus 2 is equal to 0.5 volts. So we are getting closer and closer to the threshold voltage of this NMOS transistor now. Once it gets to 2.1 volt, or VGS becomes 2.5 minus 2.1 is equal to 0.4 volts. At that point, we are at the threshold voltage of this transistor. Assume this is 2.2 volts. Then VGS becomes 2.5 minus 2.2 is equal to 0.3. So the NMOS, since its threshold voltage is around 0.4 volts, it's going to be turned off at that point. It means that we can pull the output up to 2.5 volts minus 2.5 volts minus the threshold voltage of this transistor, 0.4 volts. 2.5 minus 0.4 is equal to 2.1. So this output over here can be charged up to 2.1 volts if we use an NMOS transistor, but we cannot pull it all the way up to 2.5 volts using an NMOS transistor. So that's why we say that it's better to use PMOS transistors in the pull-up network, because PMOS transistors can pull the output all the way up to 2.5 volts. Let us erase everything over here because we would need to, and I can do it with the help of Control N to start a new MS Paint window, but then I've worked on the settings of this pencil and eraser, so I don't want to lose that because we need to come back to this later. So we cannot use NMOS transistors as in the pull-up network, because with the help of NMOS transistors we can only pull it up to the supply voltage minus the threshold voltage, which in case of 2.5 micrometers technology, if the supply voltage is 2.5 volts, we can only pull up the output to 2.5 minus the threshold voltage, which is 0.4, 2.1 volts, but not all the way up to 2.5 volts. However, if we use PMOS transistors, then we can pull it up all the way to 2.5 volts. Now consider the example of a pull down network. So initially assume that we use NMOS transistors in the pull down network, and then we will use PMOS transistors and see what happens. So let us try to do that once again in the MS Paint. So initially assume that this is the output, and we use an NMOS transistor in the pull down network, and then we have a capacitor over here, the load capacitance. Okay, here is our output. For the NMOS transistor, the source is connected to ground, and here is our drain. Here is the gate of the NMOS transistor, and a NMOS transistor conducts when the input is high, so 2.5 volts. Initially assume that the output is high, so assume that the output is at 2.5 volts as well. Now our VGS is equal to 2.5 volts minus, since the source is at the ground level, so our VGS would be equal to 2.5 minus 0, 2.5 volts all the time. This transistor would conduct all the time, and we can discharge the output all the way from 2.5 volts to 0 volts. However, if we use a PMOS transistor in the pull down network, once again, pardon my drawing. If we use a PMOS transistor in the pull down network, then here is the gate of the PMOS transistor. The drain would be connected to ground, the source would be connected to the output, and PMOS transistor conducts when the input is 0 volts. That's an awesome 0. So assume that we need to pull the output down from 2.5 volts to 0 volts. Okay. So initially our VGS is 2.5 volts, and this transistor conducts. Now it's going to be discharged to slowly to 2.1 volts, so VGS becomes 2.1 volts. Then it's going to be discharged to 2 volts, and then to 1.5, VGS becomes 1.5. And then it's going to be discharged to 1 volts, VGS becomes 1. Then it's going to be discharged to 0.5 volts, VGS becomes 0.5. This transistor still conducts at 0.5. But when it's discharged to 0.4 volts, at that point we are at the threshold level of the PMOS transistor. So below that, this transistor would stop conducting. And that's why I say that we cannot pull the output all the way down to 0 volts if we use PMOS transistor in the pull down network. So the conclusion is that the PMOS transistor produce strong ones, which means that if we use PMOS transistors in the pull up network, we can pull the output all the way up to 2.5 volts. Also, the NMOS transistors, if they are used in the pull down networks, they produce strong zeros, and NMOS transistors used in the pull-down network would help us pull the output all the way down to 0 volts. So that's why we say that PMOS transistors produce strong ones, then NMOS transistors produce strong zeros. Construction rules for logic functions. NMOS transistors connected in series, they correspond to an AND function. And NMOS transistors connected in parallel, they correspond to an OR function. Similarly, by duality principle, we can create the pull-up network as well. Similarly, the PMOS transistors connected in series correspond to an OR function, and the PMOS transistors connected in parallel correspond to an AND function. That is from duality principle, because from De Morgan's theorem we know that A or B whole complement is equal to A complement and B complement. A and B whole complement is equal to A complement or B complement. So if we are given a logic function, for example, assume the logic function is equal to A and B whole complement, a NAND function. From this NAND function, we know that the NMOS transistors are connected in series. And then from De Morgan's theorem, from duality principle, we know that if the NMOS transistors in the pull-down network are connected in series, it corresponds to the PMOS transistors in the pull-up network connected in parallel. So from the logic function, we can actually construct the pull-down network. And then from the pull-down network following the hierarchy, we can actually construct the pull-up network. Here is an example of an AND function. If the input is high, for example, if A is high, then this NMOS is conducting. Similarly, but if input B is low, then this NMOS is not conducting. So we cannot pull the output all the way down to ground unless both the inputs are high. If both inputs are high, both NMOSes are conducting, and we can pull the output all the way down to the ground, to 0. So that's how we form the truth table. On the other hand, if either input A or B or both the inputs are low, we actually make a conducting path from the output to the supply voltage, and the output would be 1. For example, if input A is low and input B is low, both of them are conducting, we have a path from the output to the supply voltage. Similarly, if input A is 0 and input B is 1, this transistor is not conducting, but this transistor is conducting, so the output is pulled up to VDD using this path. And we can also apply this principle to if the input A is 1 and the input B is 0, then we have this conducting path and the output can be pulled up to VDD. Synthesis of complex CMOS gate. How do you form circuit diagram from a Boolean function? For example, if this logic function is given, f is equal to d or a and b or c whole complement, how do you form the circuit diagram? So as I already discussed, the first thing that we need to do is to form the pull down network. For that purpose, let us start from the right. B or C, so it means that transistors B and C are in parallel in the pull down network, and then both of them are in series with A in the pull down network, and then all these three are in parallel with D transistor in the pull down network. So all these three are in parallel with D transistor in the pull down network. Then in order to form the pull-up network, from duality principle, we know that if NMOSes are in series in the pull-down network, it means their PMOSes should be in parallel in the pull-up network. So here we know that D is in series, is in parallel with these three inputs in the pull-down network. So in the pull-up network, for PMOSs, D is going to be in series with all these three transistors. Also, B and C are in parallel in the pull-down network. So in the pull-up network, they are going to be in series. And similarly, the combination of B and C are in parallel in the pull-down network, parallel together. But the combination of these two are in series with A in the pull-down network. So the combination of these would be in parallel with A in the pull-up network. So that's how we form the circuit diagram for complementary CMOS gates. Now let us discuss stick diagrams and Euler graphs. Stick diagram are actually an interface between the circuit diagram and between an actual layout of complementary metal oxide semiconductors, integrated circuits, and VLSI design. The stick diagram over here in the center convey layer information through color codes. For example, the red color over here, it corresponds to the polysilicon gate. Similarly, we are going to have NMOSs and PMOSs, and also they are represented with the help of sticks or lines. That's why it's called stick diagram. And these sticks or lines actually represent devices and conductors. Devices, for example, PMOSs and NMOSs, and conductors would be wiring and railing of the supply voltage and also of the ground. Similarly, different color codes for the polysilicon gates as well. So it's basically an interface between the circuit diagram and an actual layout of the complementary metal oxide semiconductor integrated circuits. Euler path, on the other hand, is actually a path in a graph in which we can visit the edges exactly one time, but it allows us to visit the vertices, or we can also call them the nodes, multiple times. For example, here is a graph. Now, in an Euler graph, we are required to visit each edge exactly one time, and we can visit the nodes multiple times. So we can have multiple solutions for this. The starting point is over here, and the end point is over there. Starting from here, one Euler path would be go through this edge and follow this path, and then go through these edges and follow this path, and then get to the end point. So this is one solution, and in this solution we have traversed through each edge exactly one time. However, at points we have visited the vertices multiple times. But this is just one solution. Another possibility is starting from here, then going this way, and then follow this path, and then going this way and follow this path, and then get to the end. So there could be multiple possibilities for the Euler paths. There are certain rules and regulations for the formation of the stick diagrams. First, we represent different layers with the help of different color codings. For example, the supply rail and the ground rail, they are represented with generally with blue colors. Similarly, the polysilicon gates are represented with red colors. The P plus diffusion region is represented either with yellow or orange color, and the N plus diffusion region is represented with green color. Now the question is, what is a P plus diffusion layer? The P plus diffusion layer is actually drains. It represents drains and sources in the pull-up network in PMOS transistors. Similarly, this diffusion layer, the N plus diffusion layer, corresponds to the drains and sources for the NMOSs in the pull-down network. So the P plus diffusion region corresponds to the drains and sources of NMOS transistors, and the N plus diffusion layer corresponds to the drains and sources of the NMOS transistors in the pull-down network. So the rules, according to the rules of the stick diagram, if the same layer crosses each other, it makes a contact. There are different layers, polysilicon layers, the diffusion layers. Similarly, we have wiring or conductors. So if the same layer crosses each other, it makes a contact. For example, consider this example over here. Here we have the source of A and the source of B. They cross each other. They are on the same side of the polysilicon gates. So it means that they make a contact. Similarly, the drain of B and the source of A, they cross each other, so they actually make a contact. If different layers cross each other, they don't make a contact. For example, here is the contact to the output. And this is actually the conductor layer. And this red layer over here is the polysilicon gate. These are different layers. If they cross each other, they don't make a contact. So here in the stick diagram, this conductor is not making a contact with this polysilicon gate because they are different layers. The polysilicon crossing the N and P type diffusion makes NMOS and PMOS respectively. Here is the polysilicon, here is the P plus diffusion layer, here is the N plus diffusion layer. This polysilicon crosses the N plus diffusion layer at this point, so it forms an NMOS transistor. And it crosses the P plus diffusion layer over here, so it forms a PMOS transistor over here. Similarly, we have another PMOS transistor at this point and another NMOS transistor at this point. Cross marks have to be made on VDD and VSS rails to create N and P well contacts for NMOS and PMOS devices. So if we want to connect certain points to the supply voltage or to ground, we need to make cross marks. For example, here the sources of A and B are connected together, and they are connected to VDD as well. So we connect VDD to the sources of A and B, and we make a cross mark over here. Similarly, in order to connect the source of B with the ground, we actually make a cross mark. Also, in order to make contacts to the output, we make cross marks on the P plus diffusion layer and N plus diffusion layer, like over here on the N plus diffusion layer, and also on the P plus diffusion layer at different points in order to connect these points on the diffusion layers to the output. PMOS devices must be placed in the pull-up part, and NMOS devices in the pull-down part in the CMOS design style, and that is pretty obvious. We generally do it in the circuit diagram as well. The advantages of stick diagram and Euler graph is that it gives us good density and minimum area, and we have a single diffusion strip in both wells. So, for example, consider this design. This is a good design. If we follow the stick diagram rules, and if we form the right Euler paths, then we have a single diffusion strip in for the PMOS transistors, and we have another single diffusion strip for the NMOS transistors. However, if we don't follow the right stick diagram rules, and if we don't form Euler paths, then we might have interrupted diffusion regions. For example, here we have an interruption between the P plus diffusion regions. We have another interruption or spacing over here between the P plus diffusion layers. Similarly, we have interruptions or spacing at the N plus diffusion layer as well at this point and also at this point. Now the problem in this case is that it's going to require more number of fabrication steps, and also you can see that for these interruptions we have wider spacing between the polysilicon gates. Similarly for this we are going to have wider spacing for the polysilicon gates. It's going to cost us area if we have interruptions in these diffusion strips, and area, as we know, is money in complementary metal oxide semiconductors, in integrated circuits, because we are trying to fit more number of transistors on a single chip in order to improve the functionality of our chips. So if it's going to require large area to fabricate the same number of transistors, then we will have lesser functionality. So good design in following the right stick diagram rules and Euler paths actually helps us improve the density, gives us good density. We can fit more number of transistors on the same size chip, and it makes our automation easy as well. For construction of the logic graph for the Euler path, the vertices represents the node of the network and the edges represent the inputs, and we actually make dual graphs for the pull-up network and for the pull-down network. So consider an example. Consider this circuit diagram, a NAND gate. We have one node over here and another node over here. They are connected to the supply voltage for the pull-up network. So if we want to form, and then we have two inputs, two transistors A and B. In fact, I have not formed an Euler graph for this one, so let us move to the next slide. Here we have multiple nodes. We have this node and we have this node, and in between we have transistor C. So in order to form an Euler path, we make two nodes over here and then connect them together, and this edge corresponds to, in this case I would say like the order is reversed, so it corresponds to, it can correspond to CBA, the order does not really matter, so it corresponds to one transistor. Similarly, we have this transistor, okay, so form another edge for transistor B. Similarly, we have this transistor, so form another edge. So the vertices on the Euler path corresponds to the node in the circuit diagram, and the edges correspond to different transistors, to different inputs in the circuit diagram. Similarly, in the pull-down network, these three transistors are connected in parallel. So we can form edges for these three as well. The edges correspond to the transistors or to the inputs. And the nodes, the vertices over here correspond to the nodes in the circuit diagram. And then we connect this point to the supply voltage and this point to VSS or to ground. So this is how we form the Euler path or Euler graph, in fact, because we have to decide the path later. How do you make the Euler path? Path through all the nodes such that an edge is visited only once in both the pull-up network and in the pull-down network. So for example, for this, the Euler path should be, as already discussed, the rule is we can only traverse through, we have to traverse through all the edges exactly once. So we traversed through this edge, then we travel through this edge, then we travel through this edge, and we form the Euler path becomes ABC for the pull-up network. Then for the pull-down network, we need to make sure that the same Euler pattern exists for the pull-down network as well. So we go through this edge, and then we traverse through B, and then we traverse through C. So ABC pattern also exists for the pull-down network. Since ABC exists for both pull-up network and pull-down network, so this is one Euler solution for this circuit diagram. This is one Euler path. We can also have CBA, because CBA also works for the pull-down network as well. However, we cannot have BAC, because for BAC we have to travel through this direction, but in order to traverse through C, we will have to follow this path once again. So we are not going to travel through each edge just once. We will have to traverse through edges A and B twice. So this solution does not exist. Ordering of the polysilicon gates. Order the polysilicon according to the Euler sequence. So for example, over here our Euler sequence becomes A, B and C. So the ordering of the polysilicon gates should be accordingly as well. A, B, C, or we can reverse the order, and we can place A polysilicon gate over here, B input over here, and C over here. So the ordering of the polysilicon gates should be according to the order of the Euler path. Okay, now let us try to solve a few examples of stick diagrams. Starting from the logic functions, and then we will draw the circuit diagrams, and then we will look at the stick diagrams of these. So here is our logic function, A, B whole complement. It's a 2 inputs NAND gate. A and B are in series and the pull down network, so they are going to be in parallel in the pull up network. Now in order to form the stick diagrams, it is crucial to label the sources and drains of all these transistors. We know that the source of PMOS transistor is connected to the supply voltage. So we can label them as S and D for transistor A. Similarly for PMOS B, the source is connected to VDD and the drain is connected, and this becomes the drain which is connected to the output. Similarly for the pull down network, for NMOS, our source would be connected to the ground. So starting from here for transistor B, the source is connected to be the source is going to be connected to the ground, and then we follow this order. This becomes the drain of the transistor, and then keep going and follow the same order. So this becomes the source of A, and this becomes the drain of A. Now in this case, since we just have 2 inputs, so the order does not really matter for the polysilicon gates. We can label this one as A and this one as B, or we can label this one as A and this one as B. But labeling of the sources and drains is really crucial. It helps us easily solve the stick diagram. And then once again we form the supply rail and the ground rail. This becomes our P plus diffusion strip. This becomes our N plus diffusion strip. Polysilicon gate A and polysilicon gate B. The source of B is connected to ground. So label this side as the source of B and make a contact of the source with the ground. Now if this side of the polysilicon gate becomes the source, then label this side of the polysilicon gate of input B as drain. now the drain of B is connected to the source of A. So label this side of input A as source because they are connected together. It's the same color. They cross over each other. If the same layer crosses each other, they make a connection. So the drain of B is connected to the source of A, drain of B connected to the source of A, and then the drain of A is connected to the output. So make a connection from the output to the drain of A. Now similarly, we have to make connections on the stick diagram for the pull-up network as well. The drains of A and B are connected together and to the output. So label this side. Also we see that the sources of A and B are connected together and to the supply voltage. So the sources of A and B are connected together and then make a connection of these two to the supply voltage. Similarly, the drains of A and B are connected together and connected to the output as well. Label this side as the drain of B, this side as the drain of A. They are connected together and connected to the output as well. But this is not just, there is no single solution. We can label this side as drain and this side as drain because the drains of A and B are also connected together. And then we can make a connection from the drains to the output, like from here to here. And then label this as source and this as source and connect them to the supply voltage. So there are multiple possibilities. There is not just a single way to make the stick diagram. Here is another example. Our logic function is A or B or C whole complement. So first we make the pull down network in the circuit diagram. They are in parallel with each other in the pull down network, and all of them are going to be in series by duality principle in the pull up network. And then we label the sources and drains of transistors A, B, and C in the pull down network, and also we label them in the pull up network as well. For PMOSs, the source is connected to VDD, so starting from here, this becomes the drain of C, and then source, drain in the pull-up network. Similarly, the source of NMOS transistors is connected to ground. It becomes the starting point. Follow the order, source, drain for transistors A, B, and C. Now, draw the Euler graph for this circuit diagram. These are in parallel with each other in the pull-down network, and they are in series with each other in the pull-up network. So our Euler path becomes A, B, C. For the pull-up network, it works. Now let us check if it works for the pull-down network as well. We need to make sure that our Euler path works for both pull-up network and pull-down network. So our Euler path in the pull-up network is ABC. We can also make an Euler path, the same Euler path for the pull-down network as well. ABC works for the pull-down network as well. Similarly, CBA would be another solution which works in the pull-down network as well. However, as already discussed, that BAC is not a solution because in that case we would need to traverse through these edges not just once but twice. So this solution is not going to work. So our Euler path is ABC. Let us keep the sequence of these polysilicon gates accordingly in this order. But we can reverse the order. We can label this one as A, this one as B, and this one as C as well. So both of these work. Now we already labeled the sources and drains of all these transistors in the pull-down network and also in the pull-up network. So we see that the sources of B and C are connected together and connected to the ground and connected to the source of A. So the sources label this side of B as the source and this side of A as the source. They are connected together, as we already see, and they are connected to the ground. And similarly, the source of A is also connected to the ground. So label this side okay, A and B. The sources of A and B are connected together. These are A and B. They are connected together into the ground. Similarly, the source of C is connected to the ground. So label this side of C as source and then connect it to the ground. Now similarly, the drains of B and C are connected together into the output. The drains of B and C are on the same side of the polysilicon gates, so they are connected together and then make a cross over here to connect it to the output. But also A is connected to the drain of A is connected to the drains of B and C, and is connected to the output as well. So connect the drain of A to the connection of B and C and to the output as well. This solves our issue for the pull-down network. Now we need to make connections for the pull-up network as well. The drain of A is connected to the output. This is A. Connect, label this side of A as the drain and connect it to the output. The source of A is connected to the drain of B. This side, so if this side of A is labeled as the drain, then this side automatically becomes the source. Connect the source of A to the drain of B. And then the source of B is connected to the drain of C. The source of B is connected to the drain of C. Label this side as the drain of C because we need to connect the source of B with the drain of C. And the source of C is connected to the supply voltage. So now we have formed the entire stick diagram for this logic function. Consider another logic function, A or B and C whole complement. B and C are in series in the pull-down network, and the combination of these two is in parallel with A in the pull-down network. And then from duality principle, B and C are going to be in parallel in the pull-up network and in series with A in the pull-up network. And then label the sources and drains of all these transistors accordingly. The principle is the starting point should be the source of the NMOS is connected to the ground, and then follow the order. Similarly, in the pull-up network, at the starting point, the source of the PMOS transistors should be connected to the supply voltage, and then follow this order all the way to the output. So now we form the Euler graph, and from there we determine the Euler path. So here is the Euler graph for this circuit diagram. And the Euler path could be ABC in the pull-up network, and ABC also works in the pull-down network. So this is ABC as one solution. Another solution is CBA. It works in the pull-up network, and CBA works in the pull-down network as well. However, BAC is not a solution, because for BAC we have to traverse through B edge and then A edge. However, in order to traverse through C, we will need to revisit this edge the second time, which violates the basic laws, the basic rules of Euler paths. And according to the basic principles, we need to traverse through each edge exactly one time. So the Euler paths are ABC and CBA. Let us try to solve it with ABC. So A or BC, where is A or BC? It's the same thing. So moving on to the next slide. Our Euler, no, this is different from the next one. Okay. So let us look at this circuit diagram. The sources of A and C are connected together, and they are connected to the ground. So in the stick diagram, the sources of A and C, they are connected together into the ground as well. So if this side is labeled as the source, then this side becomes the drain. Similarly, this side of A is labeled as the source. This side becomes the drain. Now the source of C is connected with the the drain of C is connected with the source of B. The drain of C is connected with the source of B. So if this side is labeled as the source, this side becomes the drain of C. Okay, and the drain of C needs to be connected with the source of B. So label this side as the source of B. Then this side automatically becomes the drain of B. And this side automatically becomes the drain of A. And from the circuit diagram, we see that the drains of A and B are connected together into the output as well. The drains of A and B are on the same side of the polysilicon gates, so they are automatically connected together, and make a cross mark over here in order to connect it to the output as well. Now we need to make connections for the pull-up network as well. The drains of B and C are connected together and into the output. The drains of B and C are connected together into the output. So label this side of B as the drain and this side of C as the drain, because they are connected together, so they should be on the same side of the polysilicon gates, and make a connection from these drains to the output. The sources of B and C are connected to the drain of A. The source of B should be connected to the drain of A, and similarly we need to make a connection from these to the source of C as well. The source of A should be connected with the supply voltage, the supply railing. Label this side as the source of A and make a connection from here to the supply voltage. So this forms our stick diagram for the logic function A or B, C whole complement. Now we got another logic function A or B and C whole complement. So A and B are in parallel in the pull down network, and the combination of these two is in series with C. And then from duality principle we can form the pull up network as well. Similarly we label all the sources and the drains, and then we form the Euler graph. The Euler path solution is A, B, C in the pull up network, and A, B, C also works in the pull down network as well. Similarly CBA would also work, because CBA would also work in the pull down network as well. However, we are going with ABC Euler path. So we draw the polysilicon gates ABC. We make the P plus diffusion layer, the N plus diffusion layer, the ground rail and the supply rail. And from here we see that the sources of A and B are connected together and to the ground. So label this side as the source of A as the source, and label this side of B input as the source. They are connected together, and make a connection from these two to the ground as well. And if these two are sources, then the other two becomes the drains. The drains of A and B should be connected together. Make a connection from the drain of B to the drain of A, and these two are connected to the source of C. So label this side as the source of C. We already made a connection from the drains of A and B to the source of C. And then if this side is the source of C, this side automatically becomes the drain of C. The drain of C should be connected to the output. So make a connection from the drain of C to the output. For the pull-up network, the drains of B and C are connected to the output. So here is polysilicon B, here is C. Label these sides as the drains of polysilicon gates B and C. They make a connection together, and then make a connection from these two to the output. The source of C is connected to the supply voltage. Here is the source of C, make connection from here to the supply voltage. The drain of B is connected to the source of the source of B is connected to a drain of A. The source of B, this side is the source of B. Label this side as the drain of A in order to make a connection from the source of B to the drain of A. And then the source of A is connected to the supply voltage. So finally form a connection from the source of A to the supply voltage. This completes the stick diagram for this logic function. Now consider more number of inputs. So here is another function on slide number 31. AB or E or CD whole complement. So in the pull down network, A and B are in series, and the combination of these two is in parallel with E, and then they are in parallel with the series combination of C and D. And from duality principle, we can also make the pull up network. Then we label all the sources and the drains, and for this form the Euler graph, and from the Euler graph then we need to make Euler paths. So one Euler path could be A, B, E, D, C for the pull-up network, and A, B, E, D, C also works for the pull-down network. Another possibility could be C, D, E, B, A. C, D, E, B, A is another possibility. But let us work with this Euler path A, B, E, D, C. We label the polysilicon gates in the same order as the Euler path A, B, E, D, C. And then we make the supply rail, the ground rail, the P plus diffusion layer, and the N plus diffusion layer. And then from here we see that the sources of B and E are connected together. So label the same side on B and E as the sources, and then they are connected to the ground as well. And similarly, the source of C is connected to the ground as well. So label this side of C as the source and connect it to the ground. Now this side would be labeled as the drain of C. The drain of C is connected to the source of D. So label this side of D as the source. They are connected together. Then this side automatically becomes the drain of D. The drains of D and E are connected together into the output. So label this side of E as the drain. They are connected together, and make a connection from these two to the output. The drain of B is connected with the source of A. This side becomes the drain of B. Label this side as the source of A. So they are connected together. And similarly, the drain of A is connected to the output. So make a connection from the drain of A to the output as well. This completes our formation of the stick diagram process for the pull down network. Let us try to do it for the pull up network as well. The drains of D and C are connected together and connected to the output as well. Here are inputs D and C. Label the same sides as the drains, and then make a connection from these to the output. So if this side of C is labeled as the drain, this side becomes the source. And similarly, if this side of the drain is labeled as the drain, this side becomes the source. Now, the source of C is connected to the drain of E. So, and similarly, the source of D is connected to the drain of E. So this side is the source of D. Label this side as the drain of E in order to automatically make a connection between these two, and then connect these two to the source of C over here. The source of E is connected to the drains of A and B. The source, this side is the source of E. It is connected to the drain of B, label this side as the drain of B. And these two are connected to the drain of A. So make a connection from here to the drain of A as well. And then the sources of A and B are connected to the supply voltage. So make a connection from the sources of A and B to the supply voltage. This completes our stick diagram for this logic function. Then we have this example. I'm not going to follow the entire process for making the stick of the circuit diagram and the stick diagram. The crucial thing is forming the Euler path. So let us mostly focus on the Euler path. Here is our logic function, y or z or v and w or x. So form the circuit diagram accordingly, form the pull down network and the pull up network. And then some people like to form the Euler path of the pull down network vertical and the Euler path of the pull up network horizontal. I don't really like this style. I don't like the previous style, but anyhow, here is another representation of what you will see for Euler paths for stick diagrams. So let us look at this as well. So the Euler path becomes x w y z v for the pull down network, and this x w y z v also works for the pull up network as well. Similarly, another solution would be x w y z v. I mean, this is the same solution, but we can find other Euler paths as well. Like for example, wx yzv works for the pull down network, and wx xwyzv works. Okay, the first Euler path works, so let us focus on that. So this is the Euler path solution. Then label the polysilicon gates accordingly as xw yzv, and then solve the stick diagram by labeling the sources and the drains of all the transistors, and then labeling sources and the drains on either side of the polysilicon gates for the N plus diffusion layer and for the P plus diffusion layer. Here is another example. The logic function is A or C and B or D and EF. So form the circuit diagram and then form the Euler graphs, and the Euler path becomes A C E F D B for the pull down network, and this works A C E F D B works for the pull up network as well. So label the polysilicon gates in the same order as well, and then complete the stick diagram by labeling the sources and the drains on the stick diagram and also on the stick diagram and also on the circuit diagram. Here is another scenario. As I already told you, here is a bad design. If the stick diagram rules are not properly followed, then we can see this kind of scenario in which we see interruptions between the diffusion strips. So here we have two interruptions for the P plus diffusion strip and two interruptions for the N plus diffusion strip. As already discussed, there the disadvantage of this kind of layout is that it requires more fabrication steps, and it occupies larger area as well. So let us try to form the circuit diagram from this stick diagram, and then from the circuit diagram find the Euler paths, and from the Euler paths find then draw the stick diagram once again so that our P plus diffusion strip is connected, and we also find an N plus connected diffusion strip. So from here we see that the sources of D and C are connected together. So if the sources are connected together, it means that they are in parallel. Similarly, the source of E is also connected with the source of D and C. So it means that all these three transistors in the pull-down network are in parallel. So draw these three transistors. The source of D is connected to the ground, the source of E is connected to the ground, and the source of C is connected to the ground. Now let us focus on C at the moment. The drain of C is connected with the source of B. It means that these two are in series. The drain of C is connected with the source of B. It means that these two are in series. And then the drain of B is connected to the output. So make a connection from the drain of B to the output. Now let us focus on D and E. D and E. The drains of D and E are connected together. Okay. So it means they are in parallel. The drains of D and E are connected together, so it means that they are in parallel. And the combination of these two is connected to the source of A. So the combination of D and E are connected in series with A. The drains of D and E are connected in with the source of A, so it means that the combination of these two are connected in series with A. Then the drain of A is connected to the output. The drain of A is connected to the output. It forms the circuit part for the pull-down network. Now let us focus on the pull-up network. For the pull-up network, we can start from VDD. So the sources are we don't really need to in fact we don't really need to make the full pull-up network by looking at the stick diagram. We can just follow the duality principle. From duality principle, B and C are in series over here, so they should be in parallel in the pull-up network, and the combination of these two is in parallel with the combination of these three, right? And then D and E are in parallel over here, so they should be in series in the pull-up network, and the combination of these two is in series with A, so they should be in parallel with A in the pull-up network. So we don't really need to look at the stick diagram in order to form the circuit diagram for the pull-up network. My bad, I was about to do that, but then I realized we don't really need to do that. Okay, so we formed the stick diagram for this logic function, and then from the stick diagram we form the Euler graph, and from the Euler graph we find the Euler paths. So here is for the pull down network, the Euler path becomes A, B, C, D, E. A, B, C, D, E becomes the Euler path. But does it work for the pull up network? No, it does not work for the pull up network. So our Euler path then becomes E, D, A, B, C. It works for the pull down networks. E, D, A, B, C also works for the pull up network. So this becomes our Euler path. But another solution for that could be A, B, C, E, D. Works for the pull down network. A, B, C, E, D. It works for the pull up network as well. So so far we got two Euler paths, two solutions for the Euler graphs. From here we can form the stick diagram once again, the connected stick diagram. So we need to label the polysilicon gates in this order now, E, D, A, B, C, and then label all the sources and the drains in the circuit diagram, and also on the stick diagram. And from here make the connections for the NMOS transistors and for the PMOS transistors. So now we found a stick diagram which has connected diffusion strip for the PMOS transistors for the pull-up network, and it also has a connected diffusion strip for the pull-down network as well, which is the right choice of stick diagram as compared to the previous one, which is not good because it has interrupted diffusion strip. It's going to occupy more area and it's going to require more number of fabrication steps. Another stick diagram from here, from here we can also form from the stick diagram. We first form the stick diagram, and from the stick diagram we can also form we can also determine the logic function, which is A and D or E, or B and C. So we found one Euler path solution for this circuit diagram. The other Euler path solution is ABCED. ABCED. It works for the pull-down network. ABCED also works for the pull-up network. So label the polysilicon gates accordingly, and then label all the sources and the drains on the circuit diagram and also on the stick diagram, and from here we make the connections in order to complete the stick diagram. So we got two choices over here for the Euler paths. That concludes the lecture for today, and I will see you next time, inshallah.